The first one. What's the domain? What's the definition of the domain? Yeah, Jessica?
Set of inputs.
Set of all the inputs. There they all are. There's 4 of them, and they're all listed. And then the definition of the range then? Chloe? All the outputs. Set of all the outputs. Okay, and there they are. It's just a listing. Okay. So it's kind of easy to say it tends a function. It's easier to talk about 11 and why it's not a function. Okay. Or no, they're both functions, aren't they? Yeah, I picked the wrong one. They're both functions. What would make it not a function then?
If there are only 3 inputs and 4 outputs.
Yeah, I suppose that would work too. Yeah. As long as we make sure that all outputs are being pointed to. Or what could I do to number 10 to make it not a function? Could I draw in there?
Give -6 another output.
So I'll draw to another output to 2, and so now it's not a function anymore because one input has several outputs. This one, you might see this output and say it has 2 inputs, 2 things go to the same output. But that's not the definition. The definition is that every input has exactly 1 output. And even though these both go to 1, this only goes to one thing, this only goes to one thing. And it states it right here, the input -1 goes to -1. It also goes to -5. How did you guys graph this function? What steps did you take?
I started with the -1 and then went down 3 and over 4.
Okay, so you remember mx plus b slope and y-intercept. So that's definitely something you can do. That's what we'll want to do here soon. So you can start the y-intercept of -1 and follow this negative slope of -3/4. Go down 3 and to the right 4. What if you didn't know that? What if you didn't know mx plus b slope intercept? Yeah, slope and intercept. Well, let's talk about what this is. This graph, just like this set of ordered pairs and this mapping diagram, this set of ordered pairs, is just a representation of what kind of output you get for a given input. So we list an input and an output together, and a graph is a way to do a lot of those, to show a lot of those inputs and outputs, rather than a scattered group of ordered pairs. We show them on the graph. So for every input, you go down to where the graph is, or up if it's up. So for 3, you go down here, it looks like you get -3 1/3 maybe. If you go back to -2, looks like you'll get +½ Go back to -3, looks like +1 1/3 -4, +2 -3.5 goes up to, you kind of have to approximate, but that's what it's for. It's just a graphical representation. And actually, if you were to just plug in values for x and plot those points, like if we plug in 0, this is x is 0. We put in 0 for there, 0 times -3/4 is 0, -1, we get -1. If we plug in 4, -3/4 times 4, the 4's will cancel, we'll get -3, -1, -4. We did -4, -4 cancel, leaving a +3 -1 is 2. You can do that for all the points in between. You could plot those points and all the points in between. And if you could find all the inputs and outputs and put them really close together, plot all these points, that's what makes the line. A line is a bunch of little points just all the way up and down representing all the input-output pairs. Okay. So for any function that you want to graph, that you don't know what it looks like, you don't know that it's a line, what can you do? For absolutely any function, if you want to get an idea what the graph looks like. What does this point on the graph represent?
Input and output.
An input and an output. What does this point represent?
Input and output.
An input and output. How about this one? Any point on the line, or whatever the graph looks like, represents an input and an output. So what do you need in order to know what points are on the graph? Input and output. How do we find these inputs and outputs?
Put numbers in.
What's that?
Put numbers in.
Put numbers in. Which numbers?
Doesn't
matter. As long as they're in the domain, like we don't have any problem, like we don't try to take the square root of a negative number or divide by 0 or something. Yeah, you can multiply anything by negative 3/4. So you just plug something in there and see what you get out. It's nice to know that the y-intercept is -1 and the slope is negative 3/4. Because for one thing, if you try to plug in 1, you'll get 1 times negative 3/4, which is negative 3/4, and you have to do -1 minus 3/4. And it's not as nice to graph -1 and 3/4. But you could. It's just not as exact as if you're on the grid lines. So for any function, if you don't know what it looks like, as we go through these new functions, keep in mind, this is why I said at the beginning, take note of the terms input and output. And then a function turns input into output. And then all these representations are input versus output. This is a table of values is input and output, and a graph, most popular of all, is just input and output. Okay. That seemed to go well. Any questions from any other homework problem? All went well? Yeah?
I was kind of confused on describing whether it was linear or non-linear.
Okay. So like which problems?
Well, 44.
44, and we're into point 1. Okay, well 44 is not exactly to tell whether or not it's linear, right? It's just using a function. How about function notation? Did function notation confuse you guys at all? Just one person? Kind of confused you? Okay, well, make sure to let me know that before we take off, and I assume you know about function notation because it was in this section, right? Okay. So first we'll just talk about the linear thing again, just since that was the first thing that got brought up. If you can write a function in this way, and whether I write f of x or y, they're the same thing. Doesn't really matter. Either way you want to go, they both can work. If you can write it as a number times x plus a constant number, then it's linear. This is a linear function. That's all right. Does mx plus b look familiar? Why does it look familiar? What does it remind you of? Slope. Slope and y-intercept. If you remember that from your algebra or maybe your geometry class. So slope and y-intercept, that would imply that we're talking about a line. We talk about lines having y-intercepts and slopes. And that's why it's called linear. Because if you graph this, it will always be a line, as long as it's a number times x to the first power plus b. It might look like something else to start with, but if you can get it to look like this, it is linear. Okay. Maybe this. Okay, does that look like mx plus b right now? No, it doesn't look like it right now. Maybe part of it does, but in general it doesn't. But if we can get it to look like that, then yes, we could call it linear. Can we get this to look like that? A number times x plus another number. How do we do that?
You could distribute.
Distribute. Let me just combine like terms. X minus 9. And there it is. Mx plus b. So yeah, it is linear. And if we see x squared or x to the third, that's out. If we see x in the denominator or something, that's out. That's not going to be linear. This has got to be a number times x plus another number. Okay, so function notation. So as I alluded to there, f of x and y are the same. They're exactly the same. Okay? Because what they both represent, I'm going to have you see if you can think what the answer to this is. In a function, you're used to seeing x and y. What does x represent and what does y represent? Typically. X is what?
X typically represents the input or domain.
Okay, so x doesn't represent the domain, but it does represent input, and then all of the inputs are the domain. Just be as picky there. But beautifully put, yeah. X typically, it represents the input. That's where you put things into the function, and so y represents the output. Isaiah, you could move up and get closer to everybody if you feel like it.
One is there.
You can just, or you can sit there. It's up to you. Yes, so x represents the input, y represents the output, y represents the output, f of x represents the output. That's its job. That's what it does. That's how it works. It's how it functions. It's how it behaves. It behaves just like y. Okay, so you're not going to multiply this f times x. That's not what that means, though I understand that it seems like that because there's parentheses there and you're used to that. Okay, it doesn't mean that at all. What it means is just y. Whatever y means to you, that's what f of x means. It just is the output. And the reason why we use f of x instead of y is, here's one reason. Here's a function, here's another function, here's another function. Okay? There's 3 different functions. And if I want to stand over here and talk about them, I've got to point to them, I've got to be specific. I can say the one on the top, the middle one, the bottom one, or whatever. I've got to specify in some way which one I'm talking about. So if I say, put 2 into that function, which one? I got to specify. So this is one of the reasons why we use function notation is we no longer have to specify. It's the same reason that we all have different names, or at least we try to have as many different names as possible, so that if you need to refer to somebody, or if I need to refer to somebody, to a teacher, I can say, hey, did you talk to Jessica today? Now I don't have to say that girl with the brown hair, and today she has black. No, you just say Jessica, and she knows, she can at least narrow it down to all the Jessicas. Okay, so we give them names like F and G and H, or whatever you want. R, P, Q, doesn't matter. You just give them a name represented by a letter. Okay. So the other part of it is that it's a function of x. Now, it doesn't have to be x. Like Ian said earlier, x typically represents the input, but x could represent, or the input could be represented by r. The thing you'll expect to see, if you see r there, there should be an r over here. If there's an x here and an r there, it doesn't make any sense. Because this is telling you you're going to put stuff into r, so you should see places where r exists so that you can plug things into that input. And that's exactly what this means. This is just what goes into the function, the input of the function. Right now the input is r, okay, so it's a variable, it could be anything. But if I say h of 3, now what's the input? 3. And where does it go? Or whatever the variable is, the input variable in H. Not G, not F, just H. 2 times 3 minus 6 equals 0. So we would say H of 3 is 0. And that says a lot of things that we used to not be able to say with so few words. If I had this function, y equals 3x minus 17, I would have to say, when I put 1 into this function, y, you could call this function y, then I get negative 14 for y. And that was a lot of words. But if I call it f of x, well, not f, but there you have it. So f of g, let's call it r of x. And that's r of x. So instead of saying when I put in 1 I get negative 14, I can say r of 1 is negative 14. Maybe you're not amazed or impressed by that, but that is why function notation is the way it is. It's how we use it. That's what it does. So don't get mistaken and think that it's multiplication. There's no multiplication. A lot of times I'll say, what's h of 3? And I'll see like a 3 put outside here and multiplied by 3 and distribute the 3 into there. It's not multiplication. It's just the substitution of that number for that letter. How's that better? Okay. Any other questions from the homework? Okay, let's pass in the homework, please. You get Reese's work? Reese passes work in?
I think he passed it.
Think so? Now we're going to 2.2, or yeah. Okay, so we're going to be interested in linear functions specifically for a couple of sections. Okay, so remind us again, how do you know, if you're looking at the equation, how do you know that equation is going to have a line for a graph? If you look at the equation, you can tell whether or not when you graph it, it'll be a line. How do you know?
It has the number of tests.
Yep. So if it is like this, mx plus b, you know that that's going to be a linear function. So let's say we have some line, and it goes through the points 1, 2, and 5, 3. Goes through those 2 points. One of the things that we'll care about for a long time from here on out in math, yes?
Can I ask if on the Y are they going by twos?
They weren't supposed to. 1, 1, and 5, 3. It said 1, 2. It meant to do 1, 2, but 1, 1. 1, 1, and 5, 3. So one of the measures of not just lines, but actually later on of all graphs that we want to know is the slope. Now it might seem weird that you might take about the slope of something like this, but, and this will be way in the future that you talk about the slope of something like this. But it does, right here, it does have a certain slantiness to it, right? So that's something for a future date for sure. But to start with, lines for sure, they have these things called slopes. How would you describe the slope of a line? What does the slope describe about the line?
Y over X.
What's that?
Y over X.
Y over X? What do you mean by that exactly? Because not just 3 over 5, right? Not just any Y over any X. Talking about it is like a measurement of the Y over a measurement of the X in some way, right?
Yeah.
So what do you mean by that?
I don't know. I guess we always just did it rise over run or whatever.
Okay, it's rise over run. But what I'm looking for, you're correct. What is rise over run? What is it describing about the line?
The slant of the line?
The slant of the line. It's a good word to use.
And the distance between 2 points.
Yeah, it does have something to say about the distance between 2 points. Between the 2 points that you might pick. Does it say anything else to you? Any other words come to mind? Okay, slant, slope. Maybe the steepness, how steep the line is. That might be another word that you could use. The nice thing about the slope is that no matter how far apart the points are, it's the same slope. It takes the same amount of going up versus going over. It's that ratio of going up to going over. It's the same for this or for this little move here, or even bigger. That way the slope, the ratio of how much you go up to how much you go over to get to another point, it's always the same. So pick any 2 points, you can find the slope. So the slope is, as we said before, the rise over the run. So the rise would be, maybe I'll make that red, and name this like that. Blue. Okay, rise. Why is this word rise used? Tristan?
Because it goes up.
Up. Rising is going up. So between 2 points, we're going to look at how far do you have to go up vertically to get to that point, and then you can't just go up, you got to go over. So what's that over piece called? The run. You run usually horizontally. You don't run up, straight up things. So how are we going to find this red distance? Vertical distance. How long is that distance? You can just look at it and see. Yeah.
Does it have something to do with like you take like the first exit minus the second exit? I mean, why is that?
Mm-hmm. It has something to do with that. It has something to do with that. But I want to like develop it. I want to get. We can see how it would apply to every single one. Emily, what did you say?
I was saying like Y1 minus Y2 over.
Okay.
X1
Now you
minus
give
X2.
names to the Y's that Jessica was talking about.
Mhm.
But with this specific example of 1, 1 and 5, 3, how would you find the distance from this point to this point vertically?
3 minus 1.
3 minus 1. Here, this distance is 3, right? Right there is 3. And this distance is 1. So if I take this big distance and take off this much, what's left is the distance between the 2 points. 3 minus 1. Will that always work no matter where these 2 points are on the graph? Always take one y value minus the other y value and you get the distance between them?
Mhm.
Yeah, that'll always work. What if one of them is negative? That still work? What if, let's see, this one is at 2 comma negative 2, 3, 5. So if we take 3 minus negative 5, will that give us the vertical distance between the two? How far is it from here to there, just by counting it off? 8, okay. Will 3, that y value minus this y value, negative 5, give us 8?
Yeah.
Because 3 minus negative 5 is 3 plus 5, and that's 8. So, yeah, it'll work even if those values are negative, it'll work. And likewise, this should have been. Likewise, in the denominator, and if we need to stay consistent, we're trying to go from this point to that point. So we'll take the n, the final minus the initial, 3 minus 1. Okay. So how would we find the distance from here to there? 5. That x value, right? This x value is 5, and this one is 1. And so to get from here to there, you can just take this big distance 5 minus this little distance 1, and you'll get 4, the distance between the two. So 5 minus 1, get 2 over 4, 1/2. Which means that if we start at any point and we go any ratio of 1 to 2, whether it be 1 to 2, like up 1 and over 2, up 2 and over 4, up 3 and over 6, up 4 and over 8, we'll always line right back on the line. We'll find another point on the line if we move up at that ratio. That's the slope. Is that familiar? You guys remember slope? Okay. So now, in general, just so that we don't just memorize things, but we understand what's going on, I'm going to get rid of the specifics, specific values. Get rid of that. We're going to generalize it. Okay, so all of this stuff goes away too. All these specific values. So this is just some point, let's call it the first point, and this is just some other point, let's call it the second point. This point has an x and y value, this point has an x and y value. We can't just say x and y, because that's confusing, because they're different. So how do we distinguish this x from that x?
X1 and X2.
Right, we give them the names x1 and x2. And likewise, y1 and y2. So that's where it comes from. The x1 and y1 come from the same point 1. These come from the point 2. So before, we took this y minus that y. So we'll do that again. y2 minus y1 over x2 minus x1. It's really important that these two come from point 2, and these two come from point 1. Now, would it matter if we switched these two? Made this point 1 and this point 2? No, it turns out it won't matter. If we went back to our specific example of 1 comma 1 and 5 comma 3, as long as we make sure that these two come from the same point and these two come from the other point, it'll always come out the same. So we could do 3 minus 1 over 5 minus 1. It'll be the same as if we do 1 minus 3 over 1 minus 5. This will give us 2 over 4. This will give us negative 2 over negative 4, which negative divided by negative is positive, so it doesn't matter. given 2 points, you're always going to do y2 minus y1 over x2 minus x1. Let's just do number 5. Do number 5, let's just find the slope of number 5. Number 5 at 2.2, page 86. Again, it doesn't matter which points you call 1 and 2, you just make sure that the y's, that it all lines up. That the points x2 and y2 come from the same point. And when we do y2 minus y1 and x2 minus x1, we need to get the same change, the same vertical change as the change between the first point and the second point. We need to use whichever point is second consistently. It doesn't matter which one you call second. So I'm going to call this one point 2 and this one point 1. Okay, so we'll get 1 minus negative 4 over 5 minus 8. So 1 plus 4 is 5. 5 minus 8 is negative 3, so we have negative 5/3. So, oftentimes, there's just lots of mistakes that can happen if you're just trying to remember to plug numbers into certain places. You can switch the x's and the y's. That'll happen sometimes. You can do y2 minus y1, but you can do x1 minus x2. That can happen. There's lots of different things can happen. But if you remember, if you can imagine that picture, 2 points, x1 and y1, x2, x2, and y2. If we want this vertical distance, we've got to take y2 minus y1, and if we want this horizontal distance, we've got to take y2 or x2 minus x1. So, like I said before, what the slope tells us is that if we go up and over by the ratio that it says, we'll always wind up back on the line. So if one point is here, and we have a negative 5/3, how do I interpret that? So should the negative go with the 5 or the 3?
Either way.
Either way. It's a negative fraction which you get by negative divided by positive or positive divided by negative. It doesn't matter which one's negative. Okay? So if we were to think of the negative being with the 5, then where would we start going from this point? down, right? Because up is positive, down is negative. So we go down 2, 3, 4, 5. Okay. So we've gone down 5, so which way would we go now? To the right, 3. Okay. So we have to make one negative and one positive move for the slope to be overall negative. If we make a negative and a negative, well now it's like this, it would be negative 3 divided by negative, or negative 5 divided by negative 3, that'd be a positive 5 seconds. Or if the negative was here, with the 3, we could, now 5 would be positive, we go up 5, and to the left 3. But you can see, it's all the same, they're all collinear, meaning they're all on the same line.
Does that make the negative slope or the positive slope?
A negative slope has a line that falls. Okay, and I think it's probably because we read from left to right, from left to right, it does fall, you can see. And then positive slope will rise. But is that true? Will all negative slopes cause this to happen? Will it fall from left to right?
Some degree.
What's that?
I said at some degree.
To some degree, they'll all go from top left to bottom right. They'll all fall from left to right. How can you be so sure about that? All negative slopes will do that. How can we be so sure that all negative slopes cause falling lines? There'd be some negative slope that goes like this a little bit, rises just a little bit.
Oh, it's gonna have the negative slope.
So one of them always has to be negative, right? Either the rising or the running. So if we start here and we go down, okay, so that we went down, right? That's a negative. So the other move we make has to be positive. We gotta go to the right. So you go down, and no matter what you do, you would always have to go to the right. If you wanted a line that rises, if you went down first, which way would you have to go?
Left.
To the left. Likewise, if we go up, that's a positive move, so we have to make a negative, a leftward move. But yeah, that if you connect those dots, you'll always get a falling line, and same reasoning for rising. You always have to go up and to the right, up and to the right, or down and to the left, down and to the left. So, positive slope, rising line. Negative slope, falling line. What kind of a slope would a horizontal line have?
No slope.
No slope. What do you mean by no slope? It doesn't exist? Like,
Isn't it when zero's on top?
when zero's on top you have, okay, so 0 on top of a fraction divided by something, 3 is 0. 0 divided by anything is 0, it's always 0. So 0 divided by 3, 5, 17, negative 12, it'll still be 0, right? So let's test that out on the line with the rise versus run idea. Okay, so let's start at this point. How much are we going to go up? None, so we don't go anywhere up. How far do we go, in the running direction? To the right or to the left? 3, 5, negative 27. It's all going to be on a horizontal line. Okay. And how about a vertical line?
Undefined.
What's that? What was that word?
Undefined.
Undefined.
Because there's zeros on the bottom.
So 0 would be on the bottom, because if we wanted to find the slope of this just by looking at the line, how far would we go up? Doesn't matter. Let's say it's 5. Okay, then how far would you go over? You wouldn't go over at all. You would just stay always going up and never, there's no run. And also, it's whatever it is, it's rise over 0. Always 0. And you can't divide by 0. We say anything divided by 0 is undefined. Because at this point in math history, We haven't found any way to divide by 0, any way to talk about it, any way to define it. So it's undefined. There's just no definition in the math dictionary for dividing by 0. So a slope that's 0, if we do y2 minus 1 and x2 minus x1 and get 0, that's horizontal. And if we get 0 in the denominator, if we divide by 0, we have a vertical line. Say I have this line right here. Let's pretend it's straight. It's a straight line. Okay, so there's a point, there's a point. Here's the slope. Let's say it's A in this direction, it's B in this direction. Now if I were to draw a parallel line, what's the definition of two parallel lines?
Same slope.
Lines that don't touch and therefore must have the same slope. If I had a line that goes through this point and I wanted to give it some trajectory, some steepness, some slope, some slant, such that it never touches this line, if you were like in a car or something and you never wanted to run into this car, you'd have to drive right alongside it, do exactly what it does, including its slope. Okay. If you want to build two staircases so that the staircases in either direction never ran into each other, they need to go up just as much as they go over, the same as each other. So this needs to go up A and over B. Drawing very good A and B. Their slopes have to be the same. Parallel lines have equal slopes. And I'm pretty confident that at some point somebody's going to say that two lines have parallel slopes, or what's the other one? Parallel slopes, or equal line. Usually they say parallel slopes. Parallel lines have equal slopes. You can't have parallel slopes. Slopes are numbers. Slopes are fractions. And fractions can't be parallel to each other. It doesn't make any sense. So I'll keep correcting you whenever you say that, but it's not to pick on you, it's just to be specific. Alright, so parallel lines have the same slope, so if we look at two lines, we can find their slopes, y2 minus y1 over x2 minus x1, they wind up being the same. It makes total sense. They have the same slope, they're parallel. Okay. So now what we're going to do, we're going to look at something that maybe you already know what I'm about to ask. But just like with negative times negative is positive and distributed property, I'm going to prove it. So I'm going to try and draw two lines that are perpendicular. Try to those look pretty perpendicular. So I'm going to try and prove to you what the slope of the blue line would have to be perpendicular to the red line. So we don't have any numbers. We can't work with specific numbers and proofs. So let's say we start right here, and let's mark off the slope of this guy right here. Okay. We'll go up, say that much, and over this much. We get some other point. Well, let's just say that we have A and B, that the slope of this line is A over B. M is a letter that represents the slope. We talk about M, we talk about slope. Okay. So here's what we're going to do with the blue line. I could mark off the slope of the blue line however I wanted to, but I'm going to do it in a specific way so that that what I want happens. So the specific way I'm going to do it is I'm going to go up the length of B. B is the horizontal of this slope. So, and I can do that, right? This guy has this slope. I can go up this much. The thing that I don't know yet is how far over I would have to go. That makes sense? You know, I can go up however far I want, but the slope is defined by when you go up that much, how far over do you have to go? So here's what we're going to try and figure out. And for those of you who may know, how long would that have to be? It's going to have to be A, right? Only it's going to go, it's going in the other direction. Okay. So what we're going to try and prove is that that is A. We're going to use it using some stuff we've learned about triangles, right? Okay. Let's color in some angles, like this angle right here, and this angle right here. What is this angle between the two lines? I drew them perpendicular, right? So I designed that. What is 90 degrees? We call that a right angle. What's the angle between these two lines in the slope? 90. Rise over run definitely is a 90 degree. Also, this would be rise over run. Okay, great. What's the sum of these angles?
180.
180. All triangles, all three angles of a triangle add up to 180. Okay. And how much of the 180 is this?
90.
It's what?
90.
90. And so what do these two add up to?
90.
The other 90. Okay. So blue plus yellow is 90, right? Okay. Blue plus this angle is how much?
90.
Also 90. So how much does this angle have to be? It has to be yellow. Well, if this angle's yellow and this angle's 90,
One's
this
gray.
one is blue, or whatever that looks like. Okay. So far, well, really we have everything we need. But if we just say that the angles are all the same, do they have to be the same triangle? Exactly the same? If that's all we know, that all the angles are the same? No, we call those, what kind of triangles do we call those?
Similar.
Similar triangles. But if I have two similar triangles and at least one of the sides is equal,
The other two have to
they're what?
The other two have to be
Yeah,
equal.
the other two sides would have to be equal. We'd have congruent triangles. Well, it just so happens I drew this line so that it was B in length. And so we have similar triangles that one side is the same, this leg is the same, right? This corresponding sides are the same. So if those two corresponding parts are congruent, then all of the corresponding parts have to be congruent, including this one. So that one is A, except for it's not exactly A, is it? Because we had to go this way, right?
So it's negative.
So it's negative A. This A is positive, this B is positive, this B is positive, this A is negative. What's the slope of this perpendicular line? It's a negative slope. Specifically, it's B over negative A, so we have a negative slope. So perpendicular lines have what kind of slopes?
Opposite slopes.
They're opposite because one's positive and one's negative. But the opposite of A over B would be negative A over B. So they're more than opposites, they're opposite reciprocals. I forgot how to spell reciprocal. A-L-L-E. A-L. Opposite. So maybe you were just told that. Maybe that was proven to you. You already knew all that, but I love a good proof. So there it is. So if you find two slopes and they're reciprocals of each other, the numerator is switched for the denominator and vice versa, and there are opposites. They have to also be opposites, one positive and one negative. Then they're perpendicular. Anyone make sense that if one's positive to be perpendicular, you would have to go the other. If one rises, the other one would have to fall in order to be perpendicular to it. Let's say that this is time. So just drawing a little graph here. This is time. This is money. So you show up to your job on the beginning of the workday. How many of you have jobs? Okay. Have you guys ever heard of a job? You know what a job is?
Yeah.
How it works?
No.
Okay. You go there, you do things, and you earn money. Okay. Annette, how do they pay you? How do they pay you? What? Just hourly. So therefore, so now I won't ask you what you make. Let's just imagine that after, well, at 0 hours, how much have you made
Zero.
for that day? You made $0. Okay, so there's a point. And we're graphing this function that will tell you how much money you have after so many hours. So after 1 hour, what's the minimum wage nowadays?
It's like
Seven?
seven something.
7 something? Okay, well, let's give you a raise. Let's call it 8. Okay, so let's say $8. Okay, $8 after now. Well, there's a point right there. At input of 1 hour, you have output of $8. Okay. After 2 hours, you have how much? $16. Okay. Here, let's do this. Let's say, because this part makes it too easy. Let's erase these. Instead, let's say that at 0, you have 0. And after, we'll change the numbers a little bit. Let's say after 4 hours, you have $36. Let's just call this 36 because we can. 4 hours, 36. Well, you make the same amount per hour. You know that's a steady rise. You know that would be a line. It wouldn't rise really quickly for a while unless you had like commission or something like that. But hourly, well, after 4 hours, you're going to walk away with $36. Okay. Well, what's the slope of that line that represents how much you have after so many hours? There's a line right there. You got a point down here. You got a point up here. 4, 36. 0, 0. What's the slope of that line? Don't wait for me to come through.
1 over 9.
1 over 9? That's close. You got 9 over 1. Yeah. So, yeah, easy. It rises 36 and it runs 4. And 36 over 4 simplifies to 9 over 1. Okay. What are the units of these things of 9? What's the units of 9? $9. And 1 what? Hour. So the slope of this line doubles as, what would you call this?
Crown.
Your $9 per hour. Call that your
Rate.
rate of pay. And for anything, we could change these units to anything we want. We could change them to not dollars, but miles, and not hours, right? Time in hours. Well, not hours. Let's make it minutes. We changed it. Okay, so it's no longer $9 per hour. It's what?
$9 miles.
9 miles per minute. That's fast. anything we want.
Mhm.
Realistic or unrealistic, we could change them for anything we want. We could, well, one more example, because it is almost real life. Inches, and we'll measure time in years.
That's slow.
Huh?
It's slow.
That is slow. It's what now?
9 inches per year.
9 inches per year, and that's just the slope of the line. What the line is an input and output of years to inches, and so the slope of the line is what we call our rate of change. Slope and rate of change, interchangeable. How fast is y changing with respect to x? And I bring this one up because Hawaii moves towards Japan at a rate of 4 inches per year. So every year they get 4 inches closer. Which I don't think they feel it. They probably notice it. But eventually, Japan should watch out in a few thousand years. And this doesn't even have to be time. This can be, that's often what we do. We could do miles again. And instead of time at all, we could just do gallons. 9 miles per gallon, which some SUVs and trucks get. So, here's the story. The slope and rate of change are interchangeable. It's the change of y versus the change in x. That's what rise over run is. So whatever y and x are, that determines what rate we're talking about. Okay. Now we talked about slope. Now we're going to go to 2.3, and I'm going to graph equations of lines in a couple of different. The equations of the lines can be represented in a couple different ways that we're going to review, and we just need to know what's the best strategy for using that form to graph the line. So, as we talked about before, we can write it in this form, mx plus b. That's the standard for knowing if it is a linear equation. It's a linear function. This, as we've talked about already, this is slope. This right here, this is the y-intercept. So in the example, y equals 5x minus 3. How would we use that information, the slope and the y-intercept, to graph the line? Where?
On the y.
On the y, because it's the y-intercept, okay? And then how would we? Up 5 and over 1, right? 5 over 1 is the same as 5. So up 1, 2, 3, 4, 5 over 1. Put another point right there and connect the two. Now let's not just take it for granted that that's the y-intercept, okay? The y-intercept is, well, what does the word intercept mean?
Or it intersects the line.
Yeah.
Axis?
Huh?
Or it intersects the line.
Well, I'm asking you to define the word intercept, but then you're using the word intercept in the definition, which is hard not to do.
When your line goes through the y-axis.
Okay, intercept to go through, then? Intercept means to go through. Yep.
And also,
What's that?
when you go up,
Yeah.
you count the 0 as a line, right?
Mm-hmm.
Okay.
If you go up a unit, 1, 2, 3 units, 4, 5 units. Right, so the word intercept just means to cross, right? If I'm on the defense of a football team and I intercept the ball, it means that my path got in the way of the ball's path, and I intercepted the path of the ball and grabbed the ball out of the air. Okay? So the line intercepts the y-axis at this point. Okay. Well, what's the x value of the y-intercept? The x value of the y-intercept. 0. Is 0 the x value of any y-intercept? Of all y-intercepts? What do you think, yes or no? No? Yes? I see no's and yeses. What's a y-intercept? We'll redefine it once again. Don't look bad on me now. What's a y-intercept? There's one. How would you define the y-intercept?
When it crosses the line.
Crosses what?
The x-axis, the y-axis.
The y-axis. When your line that you're graphing, or any graph, it doesn't have to be a line, it could be a curve, but where it crosses the y-axis, it's what we call the y-intercept. Okay? So a y-intercept is a point. It's a point. It's a point on the y-axis. So let's look at all the points on the y-axis. All of them. All of them. All of them. Are there any points on the y-axis where the x is not 0?
No.
No, they all got to be 0. 0, 1, 0, 2, 0, 0, 1.5, 0, negative 1/2. They're all 0. Okay? So if the y-intercept is negative 3, when we plug in 0, what do we get out of the function?
-3.
Negative 3. Put in a 0. 0 times the slope is 0. All that's left is that negative 3. If we can write all of our equations as mx plus b, that'll always happen. You put a 0 in for x, the slope part goes away to 0, and all that's left is this one number right here. That would be where your line intercepts the y-axis. Okay. And let's look at a different slope to highlight this next point. Y equals 3/4 x minus, let's say plus 3. Okay, so we covered the y-intercept. Start up there at 3. Let's not say what the slope is. Let's pretend we don't know that shortcut. Okay. Let's just pretend we're going to put in an x and we're going to get out a y. What we're going to do is put in a convenient x. Okay. A convenient x would be one where the output is easy to graph. It's easy to graph this point. And the points that are easy to graph are the ones that are right on the grid. Right? They're right at 2, negative 7. You know exactly where that should go. Once you start getting into the fractions, it gets harder to graph. Okay? Now let's move this direction. Let's go over here. Okay, in the positive direction. So after 0, which is a nice input for x because it goes away and all you're left with is the y-intercept. What's the next number after that? It would be a good choice. We come out with a nice round figure, integer. There. We know we're going to multiply 3/4 by that x. What's a good choice for x?
1.
Okay.
4.
Why 4?
Because it'll cancel out.
Yeah, because we're going to multiply 3/4 by x over 1, if you like. Okay? We're going to put a number in there for x, and if we put 4 there, 4 cancels with 4, we don't get the denominator, and the denominator is going to be 1 times 1. So the next nice one is 1, 2, 3, 4. Okay? And when we put in 4, when we get 4 times, or 4 canceling with 4, that'll just leave 3 times 1. 3 times 1 plus 3. Okay? Well, we started, the y-intercept is 3, so we'll go up 3 more. After we put in a 4, we go up 3 more. So there we go. What's the next one that is a nice one to put in? 0, 4, then what? 8. 8's a nice one, because 8, how is 8 related to 4?
2.
It's 2 times 4. It's a multiple of 4. It's double of 4. Okay. So what kinds of numbers are the nice numbers to put in for x in this situation?
Multiples.
Multiples of?
The denominator.
of this denominator, the denominator of the slope. Okay? So that means that you're going to be going over in chunks of whatever the denominator of the slope is. The run. There's your run. You're moving over 4 each time. Okay? And every multiple you go up, you're going to go up to 4 times 2, then 4 times 3, then 4 times 4, right? And you're going to have that multiple of 3. You're going to go up that many 3s. So if we didn't know about the slope and we were just noticing that those are nice inputs to have, we would come up with that pattern. We would say, well, every time I go over 4, I'm going to go up another 3 from my previous point. 1, 2, 3. Timer's in the way. Like that. There comes our slope. So we can see, hopefully, kind of why. All we need to do is graph the y-intercept, and then go up and over whatever the slope tells us to do, and graph at a second point. And since 2 points are all that you need for a line, you draw a line through those 2 points. So what's the minimum you need to draw a line? What's that? 2 points. Okay. One of the ways to get 2 points is to know the y-intercept, that's a point. And then another point that you find using the slope. So there's your 2 points. Okay? Any 2 points will do. The easiest 2 points you can find are the 2 points that you should use to draw this line. Okay? So where this is called slope-intercept form, because intercept form, because you have a slope in the y-intercept. This next one's called standard, for no real reason. It's called standard form. Standard form is not y equals mx plus b, but ax plus by equals c. Where a, b, and c are all real numbers, but x and y are still variables x and y. Now let's look at the easiest way to find 2 points when we have something like this. So, let's say 3x plus 4y equals 12. Or maybe let's say 8x plus 6y equals 24. I'm going to change my mind. All we need are 2 points. We just need x comma y and another x comma y. Now this is the only way to do it. You can put in any x and any y that you want. But if we choose clever ones, our life's a little easier. Yeah?
Can't you just do the x and y intercepts? Find those?
How?
Put a 0 in for y for the x to come out?
So what's clever about putting a 0 in for y?
Cancels out?
Cancels this out. This just goes away. So that's why the book mentions finding the x and the y intercepts, because those are the easiest ones to find. If you plug 0 in for y, if we look at this table of values, you plug 0 in for y. That's clever because the y thing goes away and all that's left is something times x equals a number. We could put 1 in there, but then we'd have to subtract 6 from both sides and then divide by 8. But if we put 0, all we have to do is divide by 8. So we put 0 in for y. We get 0 here. 6 times 0 is 0. 8x equals 24. X equals 3. Same cleverness. Put 0 in for x. That goes away. And 6y equals 24, so y is 4. So we have a point at 3, 0. 1, 2, 3, comma, 0. And that's right there on the x-axis. That's what we call that the x-intercept. That's where the line intercepts the x-axis. And 0, comma 4, 0, comma 1, 2, 3, 4. We've already talked about the y-intercept. That's where it intercepts the y-axis. That's good enough. 2 points. 2, the easiest points to find. In standard form, put in zeros for x and y, because then you find the x and y intercepts really easily. In slope-intercept form, it's much easier to say, well, put a 0 in for x, that's still easy, and we find the y-intercept, y equals 3, when x equals 0. And then we have this pattern that emerges that the convenient numbers to plug in for x are multiples of the denominator of the slope. And we find soon that all we have to do is go up 3 and over 4, because those are the convenient values to plug in for x. Find 2 points, you graph the line, so all you need is 2 points. Last thing I want to talk about for lines is something that often confuses people. And that's horizontal and vertical lines and what the equations are for them. Okay. So I'll tell you that y equals something and x equals something. These are your vertical and your horizontal lines. If y just equals a number or x just equals a number, nothing else, no other variables, those two are your vertical lines, your horizontal lines. So I want you to follow your intuition here and tell me, how would you graph y equals 3? Yep.
We go up 3.
Okay, from 3 make a line. What kind of a line would you call it?
Horizontal.
Okay, so how do you, what led you to that?
If y is 3, it's on a negative 5.
Okay, why up 3 and not to the right 3?
Because y is the y-axis.
Because it's the y-axis? Okay. Because there's no x. All right. If I pick this point on this line, how do I know that this is the correct line? The equation for this line is y equals 3. How do I know? How can I be sure if this is on that line, the line for that graph?
Because the point is any x and then the 3.
Exactly, yeah. Any x, doesn't matter, I know that could be a million, or it could be 2, it depends on the scale, but the y for sure will be 3. So on this line, y needs to always be 3. For y to always be 3, we need to just cut right through y equals 3, where y is equal to 3. Just all points on the graph where y is 3. So then, how about x equals negative 2? Chloe? X equals negative 2, how would you graph that? I'm putting the pressure on. On the x-axis, where do we go? Go over 2, and draw vertical or horizontal? Draw vertical. And like the same thing that Emily said before, any point here is going to be negative 2 for sure, and then some y value. But all the points will have a negative 2 for the x. X is always negative 2. And the thing that people confuse is they see x is here, the x-axis is horizontal, and so they want to draw a horizontal line because x is horizontal. But if you draw a horizontal line, well, you're going to cut through all of the different x values, and x won't be equal to whatever it's supposed to be equal to. So keep that in mind. See if that stays with you into the quiz. See if on the quiz you don't mix those things up. I don't want you to. See if you can remember. So we're going to do 2.2, 2.3. If I remember right. These are going to be the last two in our review that we've been doing. And then we'll get into stuff that you might know, but I'll just teach it like you don't know it from scratch.